Thank you so much for introduction, Kevin. So my name is Lisa Choe. In today's presentation, I'd like to briefly talk about some results of NIST fire experiments conducted on composite floor systems. So for steel concrete composite floors, basically the concrete slab cast on trapezoidal steel decking, mostly used in the steel frame construction. The fire resistance design is basically achieved by following the prescriptive fire rating of protected steel. This method is not necessarily very cheap. We spent about like $60 million every year for fireproofing of commercial construction. And also it does not really provide technical basis for risk-informed design decisions, such as extraordinary uncontrolled fire events, because these fire ratings is basically determined using the standard furnace testing methods, where we use the specimens much smaller in size, and also the idealized boundary condition, which is less representative to the real construction. So in order to close the knowledge gaps, NIST actually recently completed the largest scale experiments, basically using this the two-story test building, as you can see from this slide, in order to measure the realistic fire performance and structural failures of rear scale composite floor systems used in the rear building, and then also to provide reliable data sets in public domain, such that the researchers, practitioners can use to validate their predictive tools and models for performance-based structural fire design. So the NIST fire test program is basically consists of 3 large fire experiments conducted on this 6.1 meter by 9.1 meter composite floor situated within this 2-story test frame. For fire condition, we basically use the natural gas burners, which we can actually create the compartment fires up to heat release rate of 12 megawatts. And also the test floor slab is actually loaded using the hydraulic actuators, with the values conforms to ASCE 7 load combination for extraordinary events, 1.2D plus 0.5 live. We already completed like all 3 experiments, but with the 3rd test is actually most recently conducted, and then we basically actually performing some post-test inspections. So this presentation mostly focusing on the first 2 experiments. The main difference between the test number 1 and 2 is actually the slab reinforcement used in the concrete slab in the test bay. Test number 1 specimen used the welded wire fabric, which is a very thin wire mesh that conforms to the minimum shrinkage reinforcement permitted in the US the construction, mostly the composite floor construction. The effective area is about like 60 millimeters square per meter slab width. And in test number 2, we basically replaced this wire mesh mat with the number 3 rebars in the both direction at 12-inch spacing. This particular the design scheme is actually used the design based on the SPM methods, incorporating the tensile membrane action. The reinforcement ratio is very similar to the ACI, the shrinkage steel reinforcement, which is 0.2% of the concrete the area. So now we are looking at the schematic of typical test floor assembly. As you can see here, the lightweight concrete slab is cast on this trapezoidal shaped steel decking, supported by the steel, the wide flange shapes. Basically, this concrete slab is acting compositely with this steel beams, actually through the headed studs. And then the support beams and guards actually protected with the fireproofing spray for 2-hour fire rating. This is the details of the slab reinforcement used in the test building. So basically, it's basically showing the 2 bays by 3 bays on the floor plan. So this is our test bay, basically reinforced with either the wire mesh mat or the number 3 rebars that I mentioned earlier. And then the surrounding bays is basically the reinforced with the number 4 rebars. And then between the surrounding bay and test bay is actually connected with this slab splice, the design, as you can see from this photograph. It's nothing but just a steel plate with the threaded bolts and nut assembly, and then also some the number 4 rebar, the continuity rebar is actually extended from the surrounding bay. The reason for this slab splice is basically we like to reuse this surrounding bay for subsequent experiments. So basically, after this portion of the floor slab or floor assembly is exposed to fire, we basically rebuild this portion of the test floor slab. So as you can see, this is the test number 2, the photograph before concrete casting. So the surrounding is basically the surrounding, the floor slab, and then we used from the test number 1, and then this portion of the test bay is basically constructed new. So this slide basically shows the concrete mixture design. I believe this is the typical the concrete mixture used in the composite floor construction with the lightweight aggregate concrete. In this particular experiments, we actually used the polypropylene fibers, FRC mono 150, just to mitigate the spalling failure that could ruin the fire experiments. But adding this this polypropylene fiber is not very typical in common construction. So this slide basically shows some, the measured properties of the concrete. So test number 1 and 2 floor specimens actually cured for 4 to 5 months before fire testing. And these bar charts basically summarize the compressive strength measured at 28 day and around the fire testing day, and also the moisture content before the fire testing. So I'd like to show you some photographs basically to demonstrate, to explain like how we apply the mechanical and fire loading during the test. So now we are looking at the top of the floor slab, basically loaded using this specially designed steel frame, which provide the uniform floor load at 24 discrete points across the test bay. And then surrounding bay is basically loaded using the water-filled the steel drum or the plastic drums, basically to simulate the 50% of the office light load. And this is the test compartment underneath of the floor slab. Basically, we used these natural gas burners that creating the intense fire condition underneath of the test floor slab. And then basically this vertical line is nothing but just the water-cooled loading tubes that connected between the loading frame at the top of the slab and then actuators at the basement. In that way, we can actually create mechanical and fire loading simultaneously. Fire experiments are typically conducted such we apply the mechanical loading at ambient temperature, which maintained constant throughout the fire exposure. So basically, this slide shows the time history of the burner heat release rate, which is basically characterizing the fire intensity, and the total actuator loads. In test number 1, the fire duration was 107 minutes, and then we actually have to remove the fire, the mechanical loading at the same time, because we saw that there's a huge, center cracks actually developed in the middle of test bay. In test number 2, the fire duration was 131 minutes, but the mechanical loading actually was continued over a 2-hour cooling period. So this test video is basically shows the fire inside of the test compartment. As you can see here, it actually creates very intense, extreme heating conditions such that the upper layer gas temperature was in excess of 1,000 degrees Celsius. And but since we did like special compartment design, considering the ventilation, thermal properties of the exposed wall, and then distribution of the burners, the upper layer gas temperature was pretty uniform across the test bay, with a standard deviation of about 30 degrees Celsius. And this plot is basically shows the comparison between the average upper layer gas temperatures measured from the test number 1 and 2 in comparison with the standard furnace temperature. As you can see, the test number 1 temperature, it was very closely related to standard furnace temperature. The test number 2 also increased in the similar fashion, but was about like 100 to 200 degrees Celsius higher than the test number 1. We put lots of thermocouples embedded within the concrete slab and also mounted on the steel beams and connections and so on to basically quantify the thermal response of these the floor assembly under fire condition. So this slide basically shows the temperatures of composite beams at midspan. So as you can see, the protected steel, the bottom, the steel beam flange and web is actually heated to in excess of 800 degrees Celsius. However, the temperatures of the reinforcement is embedded within the topping of the concrete. Above this protected steel beam, the temperature evolution was much slower and smaller. However, as you can see here, the temperature, the thermal response between the two tests is pretty comparable. And this is the slab temperature, especially away from the steel beam underneath. So basically the bottom side of the concrete slab or the steel decking is actually directly exposed to fire. And here is basically shows the test number 1 results with the orange curves, and the black curves are indicating the test number 2 results of the temperatures at different location. As you can see, given the fire condition was pretty similar, the temperature evolution within the concrete was also pretty similar. We also put like the thermocouples actually mounted on the top of the slab, basically to measure unexposed the floor temperature. And as you can see here, the top surface temperature is actually like affected by this moisture driven out from the concrete during the early phase of the fire. But once the moisture content is dry out, then actually the temperature was actually start increasing. The top surface temperature was actually measured in the range of 180 to 230 degrees Celsius from the test number 1 and 2. So now I like to play the video basically showing on the top of the slab. And then this little clock is basically indicating the fire exposure time. So this is the test number 1 video. So as you can see, following the burner ignition, this heated floor slab is continuously sag. And then also it was making lots of steam because of the evaporation of the moisture here. But around 70 minutes, we start to see the center crack actually happening in the middle of the test bay, which was actually propagating towards the longitudinal direction. Okay. So this is actually the test number 2 video with the similar view. Again, this is the fire exposure time. So as you can see, the burner, as soon as the burner ignited, you can see that the floor slab is start to sag, but the vertical deflection of this particular floor slab is actually much more delayed. It's mostly because of the reinforcement embedded within this floor slab. But even after like 131 minutes fire exposure, there's nothing much you can see from here. Okay, let's take a look at some vertical displacement measurements between the first 2 tests. So we put lots of string pots, basically measure the vertical deflection of the test floor slab. Again, the orange curves indicating the test number 1 results, black curves indicating the test number 2 results. As you can see here, the mid panel vertical displacement was reaching around 30 centimeter. We actually start to see the center crack is developing on the south of this secondary beam. Once it happened, it actually changed the displacement gradient. The displacement is rapidly increasing afterwards. However, the test number 2, the vertical deflection, the displacement actually increased in more gradual fashion, but it was actually going to all the way up to 50 centimeter. This is equivalent to more than probably L/20 ratio, the span length over 20 ratio that is permitted, that is actually used for the standard fire testing. So it's very large vertical displacement, but there's really nothing happening for that. This is basically a photograph of the top of the slab after fire, after the specimen is actually sufficiently cooled down. As you can see, the test number 1 floor slab reinforced with the wire mesh mat. Actually, as you can see that there's the large edge crack opening is happened first. And then that is mostly happened during the early phase of the fire. It's not really captured in the test video, but other video, other evidence is indicating for that one. But that really allows the large end rotation of the slab edges that actually accelerating the vertical displacement at the middle, eventually developing the crack opening at the center of the test bay. Here is the test number 2, reinforced with the number 3 rebars in the both direction. As you can see that there's a small crack openings here and there, like distributed everywhere, including some the transverse and the longitudinal lines and everything. But it actually maintained the slab continuity very well during the fire exposure. So in summary and conclusion, so test number 1 was aimed to demonstrate or create the baseline data for common US construction practice. So we utilized 2-hour fire rating for specimen design, and then also include the minimum shrinkage reinforcement. Even if the specimen is actually designed for 2-hour fire rating, we actually observed that the structural integrity failure was achieved around 70 minutes into heating. This is mostly because of the early formation of the edge crack that allows the large edge rotation of the slab, and then also insufficient ductility provided by the wire mesh mat in that particular specimen. So this experiment is kind of very important and providing very good experimental evidence that the prescriptive design is not always a safer and conservative methods. The test number 2 is mostly focusing on the influence of the slab reinforcement, how it's going to be improving the fire resilience of the composite floor assembly. So with the adequate design of the adequate amount and adequate spacing of the slab reinforcement, we can actually delay the vertical displacement and then also more effectively control the crack opening at very large vertical displacement. This project is actually internally funded NIST project as part of the measurement of structural performance in fire with the fire risk reduction building programs. We have some expert panel members invited to this project to discuss the test results and experimental design and so on. And we have the NIST and other teams actually working behind the scene to make our experiments very successful. With that, thank you for your attention, and I will take any questions from the audience.
I do have one really quick, Lisa.
Okay.
Showing the videos, you had the water that kind of formed on the top of the slab, and you had the gas coming up. What do you think would have happened if there was an actual finished floor there? Let's say a sealed tile or vinyl flooring or something that wouldn't have really cracked and allowed that to come through. Do you think that could have built up in the actual slab itself, cause other problems? Did you guys investigate that at all?
I think we really didn't consider for the floor, the finishing for that. I mean, this one, basically the moisture, here's the thing, because mostly the fire is happening in the existing building and it's been cured and dried for many, many years. So I don't know whether this kind of moisture content coming out from the concrete is very typical, but maybe it could be more relevant to the recent construction, maybe. But if we don't have this, the moisture content coming out, then it actually making the evaporate cooling on the top of the slab. So if we have much drier condition, then I guess that it actually directly hits up the floor finishing and then burning up and so on. Mm-hmm. That's what I guess.
Thanks. Any other questions? Yeah.
Hi, Lisa. Thank you very much for the great presentation. So what you showed on the first experiment is quite, striking in terms of loss of integrity well before the prescriptive rating. I was curious if you had benchmarked the amount of steel reinforcement in that design, in that baseline US design, as you refer to it, against minimum requirements in other jurisdictions, for example, in Europe. So what's the minimum amount of steel that's there in the slabs, and whether that's very different, and or you expect the same type of issues?
Oh, I think that we only basically choose the values actually specified in the Steel Deck Institute because they don't consider the thermal condition. But for normal condition, the shrinkage steel is about like 0.075% of the concrete area. So we picked that, whatever the minimum required, the shrinkage steel for that. And then that is obviously much smaller than how it actually used in the European or the New Zealand practice. But I guess that for even the whatever the fire resistance rating, the method that to determine the fire resistance rating of the composite floor in the United States, we never consider the reinforcement scheme. We only consider the thickness of the topping concrete and above the steel decking. So there's a specific, thickness that required to achieve the, the specific fire resistance rating in combination with the fireproofing applied on the steel, the members. So I think that the direction should be, I think that there's like lots of good gaps between how it actually determined the fire resistance rating and how it's performed, in the real fire conditions. So, but we didn't do any benchmarking. We just basically picked the values from the manual, the standard and codes, basically. That's what we did. If that's the questions that you're asking.
Yes, thank you. No, I fully understand where you took the design from, but I was curious if you compared that value with what is required in other codes to see whether there is a clear discrepancy, and this is clearly less than what is in other codes. But I understand why you tested that one.
Right. Obviously the values they use in the different practice, the different country is much larger. Actually, you probably know better than me for that. I don't remember the specific values for that one, but it was at least 2-3 times higher than the reinforcement used in the US practice.
Thank you.
But there's no really testing, demonstrated in the United States, what is happening for the, US construction practice. That's so why we picked that. I know that many practitioners, if there's no guidance whatsoever, they tend to use the minimum required shrinkage reinforcement just to save the construction cost.
All right, thank you.